Alright, hello everybody. Here's another video on physics. Today we're going to talk about vectors, which is a lesson about in Science 10 Physics, Unit B. So this, so if you're here or if you're watching this, welcome, and we're going to jump right in here. This is a short summary lesson. That accompanies the notes I used in the year 2024. So, yeah, without further ado, let's jump right in. So, this is lesson 2. When you're watching this video, some background you'll need is that you have taken Science 10 and have the foundations of working with mathematics, sig-dig, surrounding, measurements, and all that stuff. And of course, you're already familiar with the distance time formula, so I will be referencing those so you understand. Of course, you have some common sense about direction and stuff. Will be very helpful. So let's jump right in here. All right. So, in physics, it's very important to note that there are two type of quantities that we deal with. Okay. Now, when you're learning about distance time, how far we traveled, 5 meters, I travel 5 meters, how far, 5 meters per second. Those are all nice and good. But in physics, that's not good enough because, for instance, how far have you walked? Well, 5 meters. Yeah, normally, and every day, it's pretty good. It's pretty useful and give us lots of information. In physics, though, doesn't, because did you walk 5 meters up? Right? Did you walk 5 meters to the left? 5 meters to the right? Okay, did you go to 5 meters in space? Right? Did you throw 5 meters down into the ground? Did you throw? All those have different effect. Those are describes different kind of motion. So we need to find a way to describe those kind of motion. And the concept introduced here is concept of distance and displacement, and that leads to something else. So distance, of course, is the colloquial sense of how far something moved. Distance. Let me change the color of this pen because I actually do not like this color. Oh, wait, what's going on? One too far back. That's a previous lesson, as you can see here. There we go. Let me erase that. All right, let me change to a nicer color here. I like purple. There we go. All right, so distance, okay, so we colloquial sense how far something traveled, 5 meters. All pretty good, regardless of direction, okay? So in this case, for example, this person started here, you moved over right for 3 meters, moved left, 1, 2, 3, 5 meters, total is 8 meters, okay? Distance traveled is 8 meters. In physics, we need to be more specific, okay? We can't care about not just how far you've traveled, we want to which direction you actually started with. Okay, so we started, okay, we moved a little bit to the right, moved to the left, but in the end, we end up 2 meters to the left. I don't know why it says south here, left. Okay, we'll move 2 meters to the left, so that is what we would say in the context over here. Okay, to make this window a little bit smaller. There we go. This is more like that. Make it a little bit smaller so you can actually see more. It's on the screen. All right, like that. There we go. This is up a little bit. All right, so that's what we want. So we move 2 meters to the left, and that's sort of how we want to say in physics. We want to be very specific. We will care about where you start, where you end. The distance in between doesn't matter as much. I mean, the sort of context we do, but really care about how the object actually ultimately transitioned. Okay, so another example would be here is distance-wise. Run a distance 400 meters around a track. Okay, and a sprinter could run speed at 0.8 meters per second down a track, okay? However, when it comes down to physics, it's something more specific. Something specific, we call that a vector. A vector is something with a magnitude and direction. For instance, in the first scenario over here, Somebody would travel, around a lap, right? You run all the way around. The actual movement is zero. Actual movement is zero. We'll take a look at that closer in a little bit. Okay, so but a better example would be the concept of velocity, which we'll talk about in a little more detail. We'll say it's 1.2 meters per second east. So there's a number here and a magnitude. Okay, and here are some other examples of scalar and vector quantities. All right, so how do we denote vector quantities from the rest? All right, so what we do, of course, is distance. We will write d, distance, scalar. All right, and then we would write, okay, for vector version of it, we would write, this is not displacement yet, I know the word displacement is mentioned, but this would be a vector. I will give its name shortly. This would be what we call a vector. See a little arrow on top? That is what makes a vector a vector. All right, that's pretty straightforward. Right? Okay, we have a few viewers right now. Welcome. All right, so there it is. Okay, it's very simple. In Science 10, you'll only be dealing with one-dimensional vectors, so there's only two possible directions. Either it's, for example, north or south, okay, left or right. You'll never go like, oh, I'm going to go left, then go up, then go south, and then go turn around, and I'm going to widen that diagonally. You will learn about that in Physics 20, and it's very exciting, okay, two-dimensional vectors. You'll learn about three-dimensional, even higher dimensional vectors at university. They're very, very exciting, and you can do quite a lot of stuff with it, and there's so much more to vectors than just what I'll be presenting you today, which is like things with direction. Okay, I mean, it is what they are, but they can do so much more with it. But in Science 10, you only have two possible directions, which allow us to represent vectors in the following ways. Now, the most descriptive way is, of course, this one, to tell you literally what it is. Okay, in my Science 10 classes, I usually write my answers, and I will require my students to write my answers in this format because it's most descriptive. This is most correct because it literally write down what it is. It's most correct, so all your answers, okay, and I recommend you get used to writing answers this way because it's most clear in communicating. We'll just say 15 units left. Sometimes you want to be something visual, or sometimes you want easy to communicate. You're just drawing a diagram, right? You would use an arrow, obviously. So, mathematically speaking, okay, you can use a number. You can draw it on a number line, though it's not the most practical, so just write it down, right? Left, we're going to say, if right is positive, left is negative. This is, of course, decided by you. By the person. Okay, there's no rule that says left has to be negative, right has to be positive. It's just in its context, with reference, write down, you know what? Right is positive, left is negative, okay? And then I can write my 15 meters left as negative 15 units. This is fantastic, of course, for practical reasons. It's very easy to calculate with it, okay? However, remember, you require a reference, right? So this is still not, it is not the best way to communicate your results because somebody else may have a different reference, right? And you have to communicate your reference. So if you're going to use this, you must communicate your reference, and if you're my student watching this, okay, I will require your answer to be like this. There should be no positive or negative directions in my work, okay, in your work, if you are my student. Some other teachers may be nicer, but I just like you to be more, my students, to be a little bit more, and it's good practice for you too, to be very clear which direction you're dealing with. All right, so there are three main ways to do it. I will probably not use the number line. I'll use the other three ways, but I'll probably not use the number line directly, except for, well, occasional visual effect that you can see down here. Now, the vector I showed you earlier, D with an arrow on top, it's called position. Okay, position is sort of more like the distance that we traveled. Position of the object, like it's a vector, right? When you say, where are you? You don't say, oh, 5 meters. Like, thank you. 5 meters where? Well, 5 meters in front of the school, right? This is reference point. In front of the school, that's the direction. 5 meters north of you, right? There is a reference and a direction. Okay, so you have to be relative to an origin. Now, of course, that's going to be quite annoying, so we're not going to stay with position for too long. Okay, we're not going to stay for position for too long. Okay, but with a reference and a direction, you can talk about where your position is. It's very useful. Okay, the example down here, for instance, right? Object 1 will be 35 centimeters to the right. Vector, right? Of A, and object 2 will be 75 meters to the right. Of course, I hope I did the mental math correctly. I picked some easy numbers here. Well, on the other way around, this position of object 1 will be, 55 centimeters left. Remember, same object. The object never moved, right? But then this one will be 50 centimeters to the left. Now, exact same two objects, they never moved, but because where you decided your reference point is, their position will be very, very different. Once again, it is quite annoying. It is important. In physics, it is important to describe somebody's position. However, in describing motion, it's kind of annoying, right? It's like, oh, we want from the center to the left of B, and then you have to pick an origin. You have to specify origin. So when we describe motion, well, this is important, but this is not the most useful. We want to get something that's sort of independent of reference. Now, if you're paying attention, you'll notice no matter which reference point I pick, whether it's A or B, the actual, well, I'll use the word distance loosely here. The distance between them is going to be the same. So let's say if you have a little, I can insert shapes here. Let's say you have a ball, right? All right, and as the ball goes from here and move it over here, right? The ball moved 40 centimeters to the right. From A's perspective or from B's perspective, right? From A's perspective, they went from 35 to 75. We have to move 40 centimeters to the right. In B's perspective, they move from 55 to the left, 15 centimeters to the left. That's 40 centimeters to the right. No matter how you look at it, the movement will always be 40 centimeters to the right, no matter which reference it is. This is independent. So this concept we call relativistic. Go away. There we go. This is what we call relativistic. And we're not going like Einstein right now, relativistic. We're not talking about Einstein, and it's because if you're talking about Einstein, even the big movements here are relativistic. Okay, but this is just a classical relativistic stuff. Okay, Newton stuff. Whoa, spoilers, Newton's coming up. So there is an absolute within this relativistic concept, which is the actual quote-unquote distance traveled, and that is what we call displacement. Displacement is a change in position, and looks like that. And by definition, it's a final position minus initial position. F means final, I means initial. So let's say this is a trip, right? This is where you start. This is you end up. Now displacement will be this straight line trip from here to here. You do not care about how you get there. All you care about is where you start and where you end up. The straight line distance from initial to final. The start to finish vector. Right, so I wrote over here in the notes. You can read that. So I'll not spend too much time on it. So this is delta D. This arrow right here, delta D. All right, this is position. It's not position. There's an origin indicated, so it may not be the best representation position right here, but this vector here definitely is what we mean by displacement. So position, of course, you have to pick an origin, then you can draw the vectors, but we'll sort of hand wave that away for now. So 2 points, we start, we end up, okay, and that vector is displacement. All right, now you will notice, as I sort of suggested, we're hand waving that away, but once we actually calculate, right, we actually want to calculate displacement, we cannot hand wave that away, so we actually do need to know the starting position and the final position if they're given to us, which means we do have to pick a reference point for now to decide where our initial final is, then we can do the calculations. All right, So if they are known, then we're gonna do some really easy simple questions here. For instance, right? I didn't actually specify a direction. So since I didn't specify direction here, so let's say positive is forward, negative is backward. Okay, since I didn't specify some of these questions, just to show a point, backward. All right. So if I specify, you use what I specify. If not, use that. So a displacement from position 1, which is 45 centimeters forward from the origin, and then position 2, which is 33 centimeters forward from the position. So we know we're looking for a displacement, right? So the initial is positive 45 centimeters. The final is from, right? So this is the initial. It's from to, so that's df. So df is position 2, which is plus 33 centimeters. All right, so displacement equal to 33. Well, I should write the formula down first, I guess. So now I'm adding a lot more detail. You may be thinking, I don't need to write all this down. Well, probably you don't. Okay, probably you don't. However, it is still a very good practice. Okay, very good practice to get used to writing down all extra steps, especially when things get more complicated. Right now we're doing like the basic vector stuff. So df minus di, so 33 minus positive 33, sign is important, minus positive 35, which give us negative 12, yeah, 12, chat, it's okay, I got it, centimeters. Now once again, I do not want my answer with signs, so what we'll say displacement is 12 centimeters backwards, or back. So that's my final answer. Alright, there it is. You can try the rest of the questions if you want. If there's anything tricky about it, is to determine which one is your df and which one is your di. Alright, which one's df, which one's di. That's it. Alright, I'm gonna skip all the rest of the questions. Once again, this is a summary video. I am not going to go through all the examples here. Now, what I'll go over here is, what if you don't know the starting position and you don't know the final position. You just know some other info indirectly about what happened. Okay, indirectly. For example, you're telling you can tell you're counting a trip, right? So this is how I imagine it. Okay. The definition of displacement is more like planning a trip, right? You know where you're gonna start and where you're gonna end up, and you say, okay, this is distance, this is direction, this is how far I will go. All right. Well, the second way, which is actually interestingly enough, might be the more common way of describing a trip. It's like when you found a treasure. Okay, you're building a treasure map. Okay, so you're walking around like. I remember I start at the a tree, then I walk like 5 meters to the left, then I walk 3 meters to the north, then I turn around toward facing the sun, then I walk seven more steps. Then I start digging down 20 meters, and then there's the treasure. Okay, that's all you can do. Like you don't know where it is, right? You cannot describe where it is. Its position is unspecific, right? You can only describe where you buried the treasure. Okay? So we can also use physics, right, to figure out where the treasure actually is, okay, by basically counting all the trips together, right? If you take a trip, think of this way, right? If you took a trip, starting over here, you went over here, you went over here, you went over here, you went over here. You know what? This is not the best representation, actually. This might lead to you know what? I'll make it very simple. We're going to make it one-dimensional. Okay, two-dimensional work the exact same way. I'm not saying it's different. But so let's say you went over here, and you went over here, and then you went over here, and you end up over here, right? Just moving right and left, right? So all you did, you eventually basically went from, you started here, and you went over here, right? For displacement's sake, that's delta D, right? That's delta D. So we can basically add up, right? It's a movement on a number line, so we can just add up all these numbers, we'll get what the final number is. So we got, basically, we take the same idea. You will work for 2 dimensions as well, but you learn that in physics 20. Okay, so basically what I'm saying is, to find the total displacement, let's not subscript t here. You can also just, if I don't know where you actually start, or actually end, one or most information are missing, you can still find displacement if I know each individual displacements. Okay, this is called vector addition because you're adding vectors. Okay, so that's another way to find displacement. Okay, it's just you need to know, basically, depending on what information you know. If you're planning a trip, right, you know where you start and you know where you end up, that's the information you're working with, this will be fantastic. Okay, if you don't know where you start, or don't know where you end, you're trying to figure that out, and you're trying to find displacement first to help you figure out where the position is, then maybe you want to use the second method. Okay, depending on what question you're working with. All right, I'll do the first one over here, for instance, right? Rail drives east from Ost to Trochu, which distance 59 kilometers. Then he drives west to Sundre, and distance of 97 kilometers. What distance did Roger drive, and what's total displacement? Okay, so he's looking for total distance, total, and displacement total. That's the question asked for, and the question gave us some directions, right? So this first trip, we're going to write displacement. Displacement number 1 is 59 kilometers east. Well, second displacement is 97 kilometers west. Now, once again, just like I mentioned before, to make calculation easy, we're going to give them directions. Okay, so we're going to say east. Let's say this direction is east. East is going to be positive, and west is going to be negative. I'm going to circle that, so whoever reads my work knows. Okay, this must be indicated. So then, displacement will be the easier one here. Okay, actually, they're both pretty easy. Displacement is the easier one here, so displacement total is displacement 1 plus displacement 2, which is going to be 59 east, so positive 59 because that's east, plus negative 97. And then we're done. The value of, I'm trying to do this in my head quickly here. So 838, negative 38. What? Why is the pen not working? Pen. Follow my, there we go. Negative, what did I say? 38? Question mark? I'm a mental math at this out. Kilometers. Now we don't care about no sign, so displacement total is 38 kilometers west. Right? Distance actually is pretty easy too, as I mentioned. Distance, all you care about is no direction, so distance is just 59 plus 97. Don't forget the units, km. Yeah. Alright, this is mentally it's easier. Adding is always easier than subtracting. Okay, so there I got a 6 at the end, and then 156. No, wait. Yeah, 156. No direction, and that's distance. Alright, pretty straightforward. Okay, pretty straightforward. Okay, you can try next 2 questions as well. You may get some really interesting questions. I can combine them, right? I'll say, alright, first trip is 7 kilometers east. The total, and then starting position is like 10. Okay, starting position is 10. The total display, there's 3 trips. 5 to the 5, 5 positive 5, negative 7, and the mystery distance. Okay, the final position is start at 10. Remember, start at 10. So you start at 10. You did 1 trip to 5 to the right, 5 positive, 7 negative, and a third mystery trip. But after a third mystery trip, you end up 2 to the left, negative 2. So what's a mystery trip? I could do that, right? You may have to combine them out. So you can solve some of those puzzles, okay, by just make sure you mix up the formulas. Okay, you'll actually see some of them a little bit down. We'll talk about some more complicated stuff here. Okay, so maybe I'll do that one because now that I said it, I want to do it. So let's say you start. So position initial is 10 meters positive. Okay, to direction. All right, final position is negative 2.0. Make sure it's just meters. Okay, to make sure sig digs consistent. I definitely ignore sig digs here, but you're adding and subtracting, so it's the least decimal place. So the rounding is correct. All right. So you're still adding, subtracting, I guess. So nearest whole number should be fine. All right. But this is made up. Displacement number 1 is 2. Positive 5. Let's make positive 5. Displacement number 2 is negative 10. And the mystery trips 3. This could be my question. This could be my question, right? Then you would know, well, displacement is equal to, well, total is final minus initial, which is negative 2 minus 10. So negative 12 meters. Right? When a total displacement must be negative 12 meters. Now, we also know displacement total. I'll scroll down a little bit so you can see what's on my screen. Total is equal to displacement 1, displacement 2, plus displacement 3. Now, so to find displacement 3, we'll just go to displacement 3 is equal to total minus 1 minus 2. So total is negative 12 minus 5. And then minus negative 10. All right, negative 12 minus 5 is negative 17 plus 10, so 7 meters. So negative 7 meters, negative 7 meters, so we get negative 7.0 meters. So we got the third displacement must be 7 meters backwards, right? So this could be a question I could ask. Okay, you may have to be creative and put them together. Okay, this is a question I could ask. This is a question, I don't just ask, I asked it for fun, because it's fun, right? Hello. Hello, have a chat here. ORS, alright. But like, also it's practical too, right? If you're trying to make planning trips out and things like that. Well, I'm thinking about planning trips. I'm talking about physics trips, as in you're trying to predict the motion of an object. You're trying to set up the motion and design. So this is not something you actually do need to think about, okay? Just do a slide of bigger picture discussion here. We're only talking about displacement here for Science 10, but every single work here works for all vectors. And you will encounter lots and lots and lots of different type of vectors, things like forces, momentum, and many, many more. All vectors behaves like this. So every single down here can be applied to forces and other thing else. And usually this kind of thinking is used, imagine vectors as displacement is how we use to study how other kind of vectors behave, which is quite useful. All right, and then we're almost done. We're actually only 2 concepts away because that's easy. Okay, so then with displacement done, we can now talk about a velocity, which is the vector version of speed. And the velocity is defined as the rate of displacement. Okay, so velocity describes both the rate and direction. All right, so we define velocity as the rate of displacement. Rate of displacement. Okay, so if I since I love calculus, so the velocity is defined as the derivative, which the rate is, which gets complicated because it is little d, d over dt. However, we're not in calculus yet, so I'm just gonna pretend that you never saw that, but even though you're seeing it right now. We're gonna write down the simple version. Okay, the simple version. Now, because the velocity normally is always changing, right? Always changing, so there's no easy way to find the velocity. Okay? However, in Science 10, we're going to start focusing mainly on something we call uniform motion. And if you recall, uniform motion is something traveling at the same speed in the same direction, which in uniform motion means you have constant velocity, Somebody will tell it's not speed. It's not speed. Not constant speed. I mean, it is also constant speed. It's constant speed and direction, not just constant speed. How about? There we go. It's not just constant speed. It's constant speed and direction. So uniform motion means constant velocity. Now, if your velocity is constant, then super easy. Then velocity is just equal to total displacement over total time. That's it. That's it. Once again, only if it's uniform motion, which is most of Science 10, not all. We'll see today what happens when you don't have constant velocity, when you have non-uniform motion. Okay, but most of the time, we're actually going to be dealing with, okay, kinematics questions, at least the displacement type questions, we'll be dealing with uniform motion. Now, what is this formula actually? Well, this is the real version of the formula, which I wrote in your notes here. The real version is the average velocity. Velocity changes, right? Sometimes you drive faster, sometimes slower, okay? But you average out the entire trip. The average velocity is equal to total distance over total time. I didn't write a little t here. Okay, I should put that over there. Total distance over total time. All right? So, if you notice that, oh, wait, does that mean for uniform motion, V, the velocity is equal to V average? And you would be correct for uniform motion, right? Uniform motion means there's only one velocity. If there's only one velocity, it's going to be the average too. Makes sense, right? So if your velocity is equal to the average velocity the whole time, then you're uniform motion. I feel like it's redundant, so I didn't write it down, but I mean I did, but not in the original notes. Units, of course, displacements in meters, time in seconds, so there's your unit, meters per second. Velocity is what we call, the direction of velocity is the objects traveling in, because objects travel in velocity. So if I tell you the velocity south, which direction is the object moving? South. Okay, displacement does not tell you the direction the object's moving, because movement is velocity. Okay, movement is velocity, not displacement. So here is a very good question. Okay, once again, I will do the first example, and hopefully you can try a second example yourself. All right, so the object located, okay, 51.0 meters north of the city. It then travels, so I'm assuming this is DI then. Okay, let me write it down. So because it started there, so DI, initial position, is 51.0 meters. It then travels 27 meters per second south, okay, north, I should write north. You know what, I'd make life simple by giving direction right away. Let's say north is positive, south is negative. So this one needs to be positive, 51, saves me a little bit of time. Once again, make sure you indicate it. All right, and then travels 27.0 meters per second south. That, of course, is our velocity. So our velocity, once again, the question didn't mention any other velocity, so we're going to assume uniform motion. You're allowed to assume that for Science 10. Or you can write V average. I'm going to write V average here, because that's what the formula technically is. So V average is negative 27.0 meters per second. All right? And then time taken is 3.90 seconds. Time scalar, no direction. All right, and what's the final position? So we know the average velocity, which is the only velocity here, is equal to displacement over time, which, by the way, displacement is the final. That's because we want our actual variables in our formula. Rearrange, so that means our final position, you can take your time to rearrange. I did this quickly, so it's going to be V average times time plus the initial. And then we have everything, so we're done. So V average is negative 27.0 meters per second times 3.90 seconds plus 51, positive 51. And I don't have a calculator, I cannot do this in my head, so whatever that is, it's the answer. Because it's mixed operation, just remember it should have 3 sig digs. Alright, and that is how you can use this formula. Alright, just remember, so be careful now, the question will ask you average speed and average velocity. Average velocity is total displacement, which means you have to actually take your time and calculate everything out. While average speed is distance. Total. Okay, one, you just add the numbers up. This one for distance, you just add numbers up, which will mean always get a bigger value, right? Always get a bigger value, okay? And then delta D will, of course, is displacement. You get a smaller value because you only care about the beginning and the end. So you may say that the magnitude, okay, if you I didn't indicate this yet, okay? So we can say the magnitude, the size of V average, okay, to indicate magnitude, I'm going to use this symbol here. For those who learn math, you know this is called absolute value. If you don't know, it's called magnitude. It's a better term for it anyway. Okay, so this is called the size or magnitude. Okay, if you ever see me write these vertical lines, that's what I mean. Magnitude, which means just the size. I'm ignoring direction. Okay, so ignore direction. If you ignore the sign, the direction, right? If the magnitude of velocity will always be smaller, well, I guess could be equal, right? If there's no change, if it's distance and if in the same direction, you think, will always be less than or equal to V average, which is scalar. There's no direction, so I don't have to do the weird vertical line magnitude stuff. Okay, this is scalar, so I don't have to do that. So the size of velocity is always going to be smaller than that of average speed. They are only equal. Well, here's the question. When are they equal? The answer may not surprise you, actually. It's pretty easy. When are they equal? I'll let you think about that. If you are watching it live right now, okay, you're watching it live right now, feel free to comment what you think the answer is. So when are these two values equal directly in the live chat? All right. And that and that is one thing, one new vector. So we have displacement and the velocity. All right. This one I'm going to skip actually because most likely you'll learn. I'll talk about it. Okay, my students would have talked about it already. Because I usually teach the lab first. Okay, so I'll tell the lab first, and they would know what it looks like already. But you may not be my student. You're watching this video, so I'll go over it. So for uniform motion, okay, this one's another characteristic. I'm not going to graph this out. Okay, it takes too much time. Okay, for a summary. But if you graph the position as a function of time graph, position versus time graph. Okay, not displacement time graph, not distance time graph, position, the vector. Okay, which means could be positive or negative. Okay, could be 0 here, right? Could be negative and positive. I'm freehanding this one, so it looks like crap. Okay, I would love to produce a ruler here. Okay, but it's sort of limited in my tech. So if your position time graph is linear, if the PT, actually, why am I calling it PT? It should be DT, right? It should be DT because position is D with arrow. So the DT graph. People call it displacement graph, displacement time graph for that reason. It's called DT graph because D is position. Okay, so DT graph is, well, because the data is going to have errors, it's not going to be perfect. So you may not have like the perfect fit for your line, but if you're approximately linear, then it's probably linear. The motion is uniform. That's it. And most importantly, the slope. Okay, the slope will give us the velocity equal to, well, average velocity, but there's uniform motion, so it's also z velocity. All right. Of course, the graph could look like this, right? The graph could be negative velocity, right? It could be like that, right? Linear graph doesn't have to be increasing, right? So you can say this one that's increasing a positive slope, should moving in the positive direction. Remember, the direction of velocity is the direction of objects moving. So you can say increasing graph would be in moving in a positive direction, decreasing graph moving in a negative direction. I don't think I talk about that in my class either, so that would be good something to talk about. So once again, increasing graph, the first one I drew. Okay. Increasing graph, the first one I drew. Okay. Positive direction. This one is moving in a negative direction. But everything else works out. Alright? So slope, I'll write it down formally. I already wrote it down. Actually, I just did. I should just drag it. I'm going to write it down again. Velocity. Alright? Which is the velocity. Positive means positive direction, moving in positive direction. Negative means moving in negative direction. Boom. There we go. And if you try these questions yourselves, then I will not go over any of them, being a summary video. Okay. And last but not least, we'll wrap up today. How much time do we have left? I think we'll wrap up today. It's been quite some time. Okay. I will talk about graphs in a different video, even though it fits really nicely in here. Okay, since we already talked about graph a little bit. Oh, in hindsight, this is the downside of live streaming, despite the fact it's faster and it's easier. The downside of live stream is I cannot, go back and change what I said earlier. In hindsight, I should have not talked about the graph and talk about the graph afterwards. That's okay. So wrapping today up is to answer the question about what happened if we don't have uniform motion. Well, the answer is then you should take Physics 20. However, that answer is unsatisfying, and the curriculum of Science 10 actually asks me to give you a partial answer. So I'll give you a partial answer. So, if an object is not in uniform motion, that means there is a... Where my pen cursor go? Where'd it go? Way down there. Okay. That means there's a change in velocity. So we do not have v anymore. Boom, boom. There's no z velocity. There are different velocities. So it no longer have... So V average still, okay, so V average is still, this is fine. This is still okay, but we cannot say V equal to that because there's no V anymore. Velocity is always changing. But that's not okay. So instead, okay, instead of having one singular velocity, we have multiple velocities. Okay, usually we have a velocity you start with, the initial V, and we have a velocity you end with, right? You changed, velocity changed, final, right? And your velocity could either be increasing or decreasing, okay? Increasing or decreasing. We'll talk about speeding up and slowing down very shortly here. This picture here, I'll talk about that, okay? And then, which is defined, let me finish defining velocity acceleration first. And we call that change in velocity, the rate of change at least, not the change itself. Change itself is change. The rate of change over time to be acceleration. So by definition, acceleration is a change in velocity over time. And of course, that's just this. All right? And yes, it's only a partial answer. There are so much more. There are actually a bunch more formulas we associate with accelerated motion. Those are in Physics 20. If you're interested in learning more about accelerated motion, which is very, very, very exciting, okay, and used in math, and actually its understanding is used to understand mathematics in general, and not just in motion, in physics. Okay, this is where the attempt to study physics led to new mathematics, thanks to Isaac Newton, despite the fact he's a jerk. So anyhow, so there we go. Acceleration is that. The formula is so easy. In fact, I will go over 0 examples here, but there it is. Okay, there it is. Now, what I actually do want to go over is concept of speeding up and slowing down. Now, it's a very common misconception. Something wrong with scrolling. That positive means speeding up, negative means slowing down. That is not true. Okay, you can be positive acceleration and slowing down, and negative acceleration by speeding up. Because remember, positive negative is direction. It's not about speed. Speed is a scalar. It's about direction. So if acceleration and velocity is the same direction, you're actually making it go faster and faster. Oh, I said faster already. Make it, you're trying to change the velocity in the same direction it's already going, then you will speed up. Same direction or sign, then speed up. Alright? So in this case, for instance, this object is moving to the right. Right? Moving to the right. Alright? Acceleration is positive. So acceleration is both toward the right. Okay? Okay? In this case, acceleration is both toward the left because the sign is negative. It's positive, positive. Acceleration is negative. So, in the case where the object's moving to the right, acceleration is also moving to the right, right? Both acceleration velocity in the same direction, your velocity will, okay, get bigger and bigger. Ignore the words on here. Actually, ignore the words on there. I lied. The vector symbol should not be there. It should be increasing speed, decreasing speed, not increasing velocity. Okay? So, even though acceleration is both positive, right, increasing v, speed, not velocity, okay, even then, okay, we say, okay, even though they're both positive acceleration, this one is speeding up, and the other one is not. The other one is slowing down, even though acceleration are both positive. Similarly, if acceleration is negative, but the object's moving to the right in the opposite direction, this one will be slowing down. This one, acceleration and velocity in the same direction, right? The ball's moving left, acceleration also to the left, in the same direction. This one also be, once again, changes to V. V, textbook. I should find different images, but it's okay, small change. Speeding up as well. Okay, therefore, as we could say, acceleration and velocity are in opposite directions. Or sign that you are slowing down. So be careful. Positive acceleration does not mean speeding up. Negative acceleration does not mean slowing down. You have to look at the question. Okay, have to look at the question. Okay, I don't want to make it more complicated. Okay, so there's another phrase we use, but I'll talk about that maybe in the next video when we talk about graphs. All right, and that is vectors in a nutshell. All right, thank you for watching. Make sure you click like likes. I don't care. All right, that's it. Next time, like I said, we'll take a look at graphs. We'll talk a little bit more about speeding up, slowing down, how to study motion, how to examine motion from a more visual point of view, which is through a graph. Okay, in the next video, next lesson, okay, the video version of the lesson will come eventually. But if my student watching this video, you'll most likely see this next class, or you are watching this video for review. Thank you for watching, and I wish you have a good day. And look forward to see you in the next video in sometime in the future. Take care. Bye.